Hey, how's it going? Before we jump into the content, I just want to take a minute to thank you for stopping by the channel and checking out the content. If you like this content and you want to support more content like it, then make sure to subscribe to the channel and like this video. You can also check out the YouTube membership program and cybertrainingpro.com, where I put practice exams and other things that I couldn't put on YouTube. Again, regardless of how you support the channel and my content, I couldn't be more appreciative. Thank you so much, and let's get into the content. When the internet and TCP/IP were created, it was done so without thinking about security. Look at a lot of the protocols that we have today, like FTP, where yeah, you can require a username and a password, but an attacker can easily capture this clear text data. Luckily, as things have evolved, developers have created ways to secure data, but keep in mind that this is an afterthought bolt-on security strategy, and it's way more costly than if TCP/IP was created with security in mind from the start. And this is a theme that we still see today, where security is thought of as an afterthought and it's kind of added on at the end, which obviously ends up being more expensive. When it comes to securing TCP/IP, there's really 5 important concepts that you need to know about. Encryption, where data is scrambled and it's unreadable unless you have the decryption key on the receiving side. Integrity, meaning the data is verified and it's in the same state as when it was originally sent. Non-repudiation, meaning that a person can't deny taking an action. Authentication means that we can verify the person attempting to access data. Think of usernames and passwords. And authorization defines what a person's allowed to do with data. For example, administrators have higher privilege levels than normal users. Let's go ahead and dive deeper into these concepts. As far as computers are concerned, data is nothing but ones and zeros. But as humans, we see text, images, and things like that. All data in its natural form is considered clear text, meaning that it's not encrypted and we can see exactly what's in it, whether it's an executable or a file. When we decide to encrypt data, we need a cipher, which is a general way to encrypt data. Within ciphers, there's algorithms, which are mathematical formulas that the cipher relies on to randomize all that data. Data that we put through a cipher is called plaintext, regardless of if it's encrypted previously or not. In the real world, you might hear clear text and plain text used interchangeably. Once data runs through a cipher algorithm, the encrypted form is called ciphertext. If you're thinking back to the OSI model, encryption happens at layer 3 with IPsec and at layers 5, 6, and 7 with standards like TLS on secure websites. All other layers either can't use encryption or it's not common. Substitution is one of the earliest forms of encryption that you might see, and it involves swapping out or rotating letters of the alphabet with other letters. This is the form of encryption that you would see Julius Caesar use to send military messages, which got the name Caesar cipher, but ROT 13 is another example, which just means that you rotate the alphabet 13 letters for the key. This type of encryption is easy to crack because of word patterns, frequency of characters, and the ability to brute force it. Think about it, certain letters of the alphabet tend to show up more than others. Exclusive OR, which is also shortened to XOR, lines up an encryption key with the binary representation of data, and then it makes changes to it. As you can see on the screen, if both values are 0, the result's a 0. If one of the values is a 1, then the result's a 1. If both values are a 1, then the result's a 0. I've also included an example conversion for you. When it comes to encryption, there's 2 categories that you need to know about: symmetric key encryption and asymmetric key encryption. We're going to dive into these categories deeper, but at a very high level, symmetric key encryption uses the same key to encrypt and decrypt the data. Asymmetric key encryption uses 2 keys, one for encryption and one for decryption. Symmetric key algorithms encrypt information using a single key that can also decrypt that data with either block ciphers or stream ciphers. Block ciphers encrypt data in chunks of data, for example, 128-bit chunks of data. AES, or Advanced Encryption Standard, is the most common block cipher that chunks data into 128-bit blocks and uses either 128, 192, or 256-bit key sizes. Stream ciphers take a single bit at a time and they encrypt it, which makes these much faster to do than block ciphers. Stream ciphers traditionally have been used for very long streams of data. One of the major issues with symmetric key encryption is the need to securely share the key between parties. Asymmetric key encryption can help solve that problem. Asymmetric key encryption, or cryptography, uses 2 different keys known as a key pair, one for encryption and one for decryption. As a quick note, you might hear asymmetric key encryption, also called public key cryptography. The asymmetric key encryption process works like this. Bob first generates 2 keys, which we also call a key pair, with a public key and a private key. Bob sends a copy of his public key to Alice. This exchange can be done through email or a website download. Alice can then encrypt data with Bob's public key and sends this data to Bob. This is where asymmetric encryption can be used to encrypt a symmetric key and exchange it securely. Bob receives the data, decrypts it with his private key, and now he can read the data, and if the data is a symmetric key, then he'll have that key too. This allows Bob and Alice to use symmetric key encryption if they choose to do so. A few huge points to remember with asymmetric encryption are that data encrypted with a private key can be decrypted by the public key, and data encrypted with the public key can only be decrypted by the private key. This means that you can share the public key as much as you want, but never, ever, ever share that private key. Popular asymmetric algorithms include RSA, short for its creators, Rivas, Shamir, and Adelman; DSA, short for Digital Signature Algorithm; ECDSA, short for Elliptic Curve DSA. It's crucial that data maintains its integrity, meaning that the data received is the exact same data that was sent. Hashing is the best way to verify data integrity. You might hear it called hashing, a hash, or a cryptographic hash function, but it's a mathematical function that runs on a string of binary digits of any length that results in a value of some fixed length, sometimes called a checksum or a message digest. It doesn't matter how long the data or the input is, but the message digest will always be based on the type of hash used. Make sure that you commit to memory. Hashes are a one-way function, which means that you can't derive the data or reverse that function to see the data like you would do with encryption and decryption. Another important point is that with hashing, the value is going to be unique for that exact input value. So if you change a single letter, number, or a character, that hash result is going to be different. One common use for hashing is with software provided by developers. For example, if you go to a website and you download an executable, you might be provided with a checksum value by that developer to make sure that what you downloaded is complete and it's the correct download. Operating systems and applications can also store hashes of passwords. That way, when you enter the password, it just has to compare the stored hash value against the hash value of what you provide. This speeds up things so much, and it also prevents the need to store the password that an attacker can decrypt. This leaves attackers needing to attempt to guess passwords and hash them to compare against what they found, and it takes a lot longer. One algorithm that you might be familiar with and that's been around for a long time is called Message Digest Algorithm version 5, or MD5. Now, MD5 was introduced to the world in 1991, and it creates a 128-bit message digest. Secure Hash Algorithm, or SHA, took over as the popular choice these days. SHA includes SHA-1, SHA-2, and SHA-3. Now, SHA-1 creates a 160-bit message digest, but it does have known vulnerabilities. SHA-2 is recommended for use, and it has 6 variants. SHA-224, which is SHA-2 with a 224-bit message digest. SHA-256, which is SHA-2 with a 256-bit message digest. SHA-384, which is SHA-2 with a 384-bit message digest. SHA-512, which is SHA-2 with a 512-bit message digest. Then we have SHA-512/224, which is SHA-2 with a 512-bit message digest, truncated down to 224 bits. SHA-512/256, which is basically the same, except it's truncated down to 256 bits. Even though SHA-2 is recommended, the U.S. National Institute of Standards, or NIST, adopted a new family of hash algorithms to keep improving security in the event that SHA-2 starts having issues. That new algorithm is SHA-3. SHA-3 has 6 variants: SHA-3/224, SHA-3/256, SHA-3/384, SHA-3/512, SHA-128, SHA-256. Keep in mind that SHA-3 isn't widely used right now, but it does exist. Non-repudiation means that somebody can't deny having taken a certain action. For example, environments where accountability is huge will absolutely need non-repudiation, but a system that takes anonymous employee complaints won't have that same kind of requirement. Digital signatures are a very common thing to implement when we need non-repudiation. With digital signatures, a sender will hash a message or part of one, and then will encrypt that hash with their private key. The receiver can then decrypt the signature with the sender's public key and compute the hash of the message. If the hash the receiver calculates matches the one inside of that digital signature, then everything is good. In this scenario, the sender can't deny having sent the message unless they claim that their private key was stolen. Common uses for digital signatures are in email, trusted web browsing, and digitally signed software from a developer. PKI stands for Public Key Infrastructure and is extremely important for trusted or secure web browsing. When you go to a website with HTTPS, you'll see the padlock icon next to the URL indicating that session is secure. If you look closer, you'll see that there's a certificate for the website that includes the organization and who certifies the website as legitimate for that organization. With web browsing, you trust a third party called a certificate authority or a CA who grants these certificates to legitimate sources. Now, there's a lot of different certificate authorities, including DigiCert, GoDaddy, and many more. DigiCert, for example, is what we call a root certificate authority. Root CAs or root certificate authorities create and sign something called an intermediate certificate authority. If your organization buys a certificate, these intermediate certificate authorities will create and sign the certificate and they'll issue it to you. Because the intermediate CA assigned you the certificate, they are the issuing certificate authority. This whole structure or hierarchy is the PKI or the public key infrastructure. Authentication is the process to identify users who are trying to access data. Usernames and passwords are one of the oldest and most common forms of authentication. Unfortunately, passwords have some pretty big downfalls. For example, length is always better and they need to be complex, and you should change your passwords frequently. All of these result in users always trying to make passwords that are easy to remember, and storing passwords securely is another challenge. Multi-factor authentication, or MFA, is a strategy that requires at least 2 different factors to authenticate successfully. You might not necessarily need to know the specific factors for the Network Plus exam, but you'll absolutely need to know them for your career. And those factors are something that you know, like a username and a password combination or a PIN number, something that you have, like a smart card or a USB token, something that you are, which refers to a biometric feature like your fingerprint, and a few other factors that aren't always used are somewhere you are, which means that you authenticate based on a physical location, something that you do, where you force the user to actually perform an action like draw a pattern, some when you are, which allows you to restrict access based on factors like the time of day. Once a user successfully authenticates, the system needs to authorize or grant that user specific privileges based on an access control list or an ACL. An ACL is nothing more than a list that states permissions for a specific user. With access controls, there's a few models that you need to know about. Mandatory access control, or MAC, is by far the most restrictive and the least common, but it deals with labels that define a security level, and it's typically associated with clearances like you'll see in the military. Discretionary access control, or DAC, is a model that puts responsibility on the owner of the resources to grant access to users. The Windows operating system uses DAC on files and folders if you want to restrict access. And role-based access control, or RBAC, is very common, and it assigns permissions based on the role of a user in the environment. For example, with RBAC groups, you might have the sales department group that has access to certain sales data and everybody else can't see that information. You might also hear about network access control, or NAC, when it comes to access. This is a system more focused on what systems can do and requirements for them. For example, if a system must have antivirus software and current patch levels to actually access the network. The other models that we talked about are usually associated with users. When it comes to security for TCP/IP, it's really kind of a mess. That's because security was an afterthought after people started abusing and hacking a lot of technologies. Keep that in mind as you learn more, because security is an increasing concern in today's world. Now, back in the early days of networking, we used something called dial-up connections that communicated over telephone lines. Depending on your age, you might not even know what dial-up is, but it was very slow compared to today's standards. Using dial-up, we needed a way to authenticate systems on both sides of the connection, and PPP is one of the earliest user authentication standards that existed to connect devices. PPP, or the point-to-point protocol, lets 2 devices connect to each other requiring a username and a password, and from there, the systems can negotiate on the network protocol to use. Today, that protocol is typically TCP/IP. User authentication for PPP came with 2 different options. Password Authentication Protocol, or PAP, which exchanges the username and the password in plain text so it could easily be intercepted. And then we have the Challenge Handshake Authentication Protocol, or CHAP, which is more secure, and it relies on hashes based on a shared secret that both systems know. The chat process works like this. First, a system makes an initial connection request. Next, the authenticator system creates a challenge message. The initiating system then makes a hash using the password and sends that to the authenticator. The authenticator then compares that value to its own hash calculation based on the password. If the values match, the initiator is authenticated. Over time, CHAP keeps repeating this process to make sure that it's still communicating with that same system and that attackers haven't inserted themselves somewhere in the middle of that connection. As you might have noticed, a big difference between PPP and CHAP is that CHAP doesn't send the password over the link. Even as great as CHAP might sound, there were improvements to be made, and so Microsoft developed a version called MS CHAP in the 1990s based on the internet boom. And now we have MS CHAP version 2, which is the most secure of these protocols. AAA improves on a few key flaws with PPP. Now, a problem with PPP is that it assumes that one connection point stores all the authentication credentials. What happens if you have an internet service provider or some large organization that needs multiple modems to support large amounts of traffic? It's not practical to store that information on every single authenticator device, and we need a centralized database with this information. PPP also doesn't encrypt traffic once it gets on the network, including credentials. AAA is really more of a philosophy or a strategy than it is a protocol, because it allows us to split up some of the tasks that were all happening with one device in a protocol like PPP. Now, AAA stands for authentication, which identifies and validates the user or the system trying to connect; authorization, which grants an authenticated user or a system their appropriate level of permissions; and accounting, which tracks all the events like the logon events, usage events, and so on. There's two major standards when it comes to AAA: Radius and TACACS+. Radius, or Remote Authentication Dial-In User Service, was created to support internet service providers that connected thousands of devices using a centralized database for authentication. Radius has three components in it: the Radius server, which accesses the authentication credential database; network access servers, or NASs, that control the modems or the wireless access points; and systems that connect to the network. Radius supports PAP, CHAP, and MS Chat. Radius authentication is performed on UDP ports 1645 and 1812, and Radius accounting is performed on UDP ports 1646 and 1813. TACACS Plus, or Terminal Access Controller Access Control System Plus, is a protocol developed by Cisco, and it's used on network devices like routers and switches. Just like the modems that we mentioned, if you had to hard code login credentials for routers and switches, it would be a pain. TACACS Plus makes life easier. TACACS Plus uses TCP port 49, and it separates out authentication, authorization, and accounting into different parts. TACACS Plus also supports PAP, CHAP, MD5 hashes, and even Kerberos for authentication. Kerberos is an authentication protocol for TCP/IP networks where many clients all connect to a single authentication server instead of point-to-point. It's actually what Microsoft Windows domains use for their authentication protocol. Don't worry, you don't have to be a Windows expert, but a Windows domain is basically a network that uses a server or a domain controller running Windows Server to authenticate users in a system called Active Directory. The server also acts as the Key Distribution Center, the KDC, service, which supplies both session tickets and session keys in the Active Directory domain. Kerberos uses UDP or TCP port 88. The Kerberos authentication process works like this. A user attempts to log on, and the client system sends a hash of the username and the password to the authentication server. The authentication server, or the AS, compares the result of the hash to its own hash that it has stored. If they match, the server sends a ticket granting ticket, or a TGT, and a timestamp to that client. Now keep in mind that these tickets expire after 10 hours by default. Now the client is authenticated though, but it's not authorized yet. Next, the client sends the timestamp TGT to the ticket granting service, the TGS, for authorization. The TGS then sends a timestamp service ticket back to the client. This might also be called a token, an access token, or a session key. This service ticket is what the client uses to access any resource on the domain, and it includes the user's SID, or security identifier, and the SIDs for any groups the user is a member of. The big deal here is that the client doesn't have to keep authenticating with that server every time, which basically makes this a single sign-on protocol. Also, clients request a new token every 8 hours to avoid expiration. Now, anytime the client accesses resources, they can send the file server or whichever resource the service ticket, and if it's not expired, the user will be given access. Two really important things to keep in mind regarding Kerberos are: if the KDC goes down, nobody can access anything. It's important that you have at least 2 domain controllers that can handle the authentication. And the clocks on the network have to be accurate to maintain the timestamps accurately, typically within about 2 minutes of each other. As I've said throughout this course, the internet and TCP/IP in general wasn't considering security and protecting data when it was first introduced. Many common protocols that we have today, like FTP, HTTP, and so on, pass readable data, among other potential flaws that exist. Over time, more secure versions of these protocols started to be introduced to help increase security. Telnet is an early protocol that allowed remote access to systems, but the problem is that everything is sent in plain text and it can be read if it's captured. SSH, or Secure Shell, is a replacement for Telnet, and it allows the same kind of remote access to systems, except it protects the data being sent with encryption algorithms like RSA. SSH uses TCP port 22, and if you've ever used SSH to connect to a system, the first thing that's going to happen is the server or the system will send a copy of its public key. When the client system receives the key, it creates a session ID, encrypts all that up with the public key, and it sends it back to the server. The server decrypts the session ID and uses it going forward with data transfers. Next, the client and the server negotiate the type of encryption to use, like AES. After all of that, the user still has to authenticate, typically with a username and a password, and then they get access to the system. An alternative to using a username and password combo for SSH is the ability to use public and private keys to authenticate. This involves generating a key pair and then putting a copy of the public key onto the server and keeping the private key safe on the client system. Using this method, you can even disable passwords for SSH altogether. SSH can also create a tunnel for any TCP/IP application. Basically, the SSH connection piece is the same, but literally anything for other applications can go in the tunnel, and then it's encrypted. The image on the screen also points out a security concern with SSH tunnels because it can be used to bypass firewall rules, but we aren't going to dive deep into that for this course. Some of the protocols that exist include both authentication and encryption into a single standard. Believe it or not, online shopping and e-commerce weren't a thing before the mid-1990s. Back then, however, there was a company called Netscape who produced one of the most dominating internet browsers called Netscape Navigator, and they decided to create something called Secure Sockets Layer, or SSL. With SSL, the web server creates a copy of their certificate that they have, and they send it to clients who access that server. The client then looks at the certificate to see if it's trusted by a root certificate authority. And if all is good, the client and the server negotiate a symmetric key cipher to use for a secure session. At this point, there's an encrypted tunnel between the server and the client. Transport Layer Security, or TLS, serves as an upgrade to SSL, but it doesn't have protocol restrictions on HTTP, FTP, SMTP, and a few others like SSL does. Today, TLS is what everybody uses, but it's not uncommon to hear SSL and TLS used interchangeably. IPsec, or Internet Protocol Security, is an authentication and encryption protocol suite that works at the network layer of the OSI model. IPsec has two modes that it can use based on the application: transport mode and tunnel mode. Transport mode only encrypts the payload of the IP packet, but it leaves the destination and the source IP addresses and other IP header information in a readable form. Tunnel mode encrypts the entire IP packet, and it encapsulates it inside of another IP packet. Something great about IPsec is that it provides authentication, integrity, and confidentiality through two protocols: authentication header, AH, and encapsulating security payload, ESP. Authentication header oversees authentication and data integrity. Encapsulating security payload encrypts the TCP segment and everything that authentication header does. This basically makes ESP the protocol of choice. Let's talk about some of the secure applications that you're going to need to know about. HTTPS, or Hypertext Transfer Protocol Secure, is one that you're likely familiar with because you've probably seen it on websites that you visited, your bank, or popular shopping websites. It's indicated by HTTPS in the website URL, and your web browser will display a lock icon next to it. HTTPS uses TLS to encrypt the session for any activity on that website. You might see several different error messages when it comes to HTTPS, and those include: the certificate's no longer valid, meaning it expired, or the URL associated with the certificate doesn't match, the certificate has been revoked because it was compromised or some other issue, or the certificate is self-signed. This error happens a lot with internal applications because they aren't issued by a certificate authority. We know that SMTP, POP, and IMAP are all email protocols, but they don't really offer security built in. Fortunately, there's two protocols that allow email to use TLS. We have Simple Mail Transfer Protocol Secure, SMTPS, which might also be referred to SMTP TLS, and that uses TCP port 587. We have Post Office Protocol 3 over SSL, or POP3S, which adds a TLS wrap to POP3 email retrieval on TCP port 995. We also have Internet Message Access Protocol over SSL, or IMAPS, and that adds a TLS wrap on TCP port 993. The Secure Copy Protocol, or SCP, can be used to securely transfer data between two hosts. This is similar to FTP, but it lacks some features, and some developers recommend using SFTP instead. The SSH File Transfer Protocol, SFTP, sometimes called Secure FTP, is quite similar to FTP in that it allows secure file transfers, deletion of files, and it runs on TCP port 22. Please make sure you don't confuse FTPS, which is FTP and TLS, with SFTP because they are two different protocols. The next few protocols are protocols that you need to secure, but they're more tied to operations that make the network work and provide it with information. The Simple Network Management Protocol, or SNMP, is a protocol that allows you to retrieve information about devices like CPU usage, network utilization, and firewall hits. SNMP agents are installed on systems to collect information from a management information base at MIB, and it can send them to a central server. When this is enabled, it's quite remarkable how much information that you can actually retrieve. SNMP version 1 had serious security concerns because it would send all the data, including passwords, unencrypted over the network. SNMP version 2C also had similar issues. SNMP version 3 is the current version that includes encryption, and it's what you should use when you enable SNMP. SNMP runs on UDP ports 161 and 162. The Lightweight Directory Access Protocol, or LDAP, is a directory service that stores information like users logged on and the location of printers, just to name a few items. Active Directory uses LDAP in the background to keep database information synchronized. LDAP uses TCP and UDP ports 389. Lightweight Directory Access Protocol over SSL, or LDAPs, is a deprecated version of LDAP that you might hear about, and it used TCP port 636, but LDAP version 3 made it obsolete. The Network Time Protocol, or NTP, is another protocol that we need on networks, and it maintains the current time. Now, NTP really isn't a security concern, but authentication protocols need it to sync things up, and you want to keep accurate time so that your security logs accurately track events. NTP uses UDP port 123.